Good morning, everyone, and welcome to this webinar on accelerating and financing cities' climate plans with advanced carbon measurement. My name is Marie-Geneste, and I will be your host today together with my colleagues. So before I introduce my fellow speakers, just a few words about Everimpact. We're a team of 20 people on a mission to accelerate decarbonization with better data. We do this by measuring greenhouse gas emission using satellite, sensor, and AI for several markets. So today we'll focus on cities and transport, but we're also active in supporting clients in the maritime sector and also monitoring nature-based solutions. So let me introduce our speakers today. So I'm Marie, the Chief Marketing Officer, and I have the pleasure to be surrounded and supported by three colleagues today. Let's start with Alain.
Yes, good morning, everyone. My name is Alain Retière. I'm the CTO and one of the three co-founders of this company. My background is agronomy and tropical ecology. I've been in the remote sensing business for many years now. I was the one who created and managed for 10 years the United Nations Satellite Center, UNOSAT. And we created Everimpact back in 2015, basically to contribute, helping cities to escalate their climate action through having access to real-time CO2 emission data that make the problem more concrete and easy to see. And I'm looking forward to share with my colleagues what we do in this regard today.
Thanks, Alain. Pete, do you want to go next for intros?
Yes, thank you, Marie. So good morning, everybody. My name is Pete Hampton. So I'm head of sales here at Everimpact. I've spent my career in IT and software sales across collaboration and moved into sustainability a number of years ago. And I've got the pleasure of working with customers across the globe in a number of the sectors that we're working in, specifically cities, transportation, and our nature-based solutions offers. So thank you all for joining today. It's a pleasure to see you all on the call.
Thanks, Pete. Over to you, Tony.
Hello, everyone. My name's Tony Bush. I'm the lead data scientist on emissions and atmospherics at Everimpact. I'm an air quality specialist by background. I have around 25 years experience in that domain, in data analytics, measurements, atmospheric modeling, emissions inventory, spatial inventory mapping, and in the provision of consultancy services and support, mainly to public sector clients in the UK, Europe, and also further afield. And apologies, I cannot get my video to work this morning. Okay. It was working last week.
No worries. So what's the agenda for today? First, we will look at different approaches to reporting carbon emissions and sequestration in cities. We look at the traditional way with carbon footprinting, and we'll look at what we're doing at Everimpact, so direct measurement. We'll illustrate this by a couple of case studies, so monitoring emissions in the city of Dijon in France, and also monitoring sequestration in a forest in Japan. Then we'll look at the financial aspects, so how to use better data, better carbon data to unlock finance. And last, we'll take some Q&A. So if you have some questions during the session, feel free to put them in the chat as they come up to your mind. Now I'm going to hand over to Tony to tell us about how you can combine different greenhouse gas emission reporting techniques and how they compare.
Thank you, Marie. Morning, everyone. So at Everimpact, we've been looking at the role and the focus of carbon accounting practices over the last few years, and we've seen those practices change quite dramatically. And whereas traditionally they have concentrated on compilation of statistics on CO2 and GHGs at a national level, things like identifying country contribution, identifying national trends, contributing to national policy, regulatory compliance in general, and practices around those. What we're seeing in more recent years is a refocusing of carbon inventories on subnational scales, at cities, at regions, and particularly those cities and regions that might have net zero aspirations or want to manage their contribution to greenhouse gases. And this kind of makes sense because it's the cities and the regions that are best placed to understand the GHGs that are being emitted from their territories, and they're best place also to manage those emissions, and actually put interventions in place to reduce those emissions. So in that sense, it's absolutely right that cities and regions are starting to look at their own situation and wonder what a net zero plan, for example, should look like for my city, for their city, specifically, rather than at a national scale or a clip of a snapshot of a national scale, and also ask questions around how can I achieve my net zero plan if I have one in place, and for my city or my region, what are the low-hanging fruit? What should I tackle first? What can I get the most bang for my buck out of if I invest in an intervention to reduce carbon emissions, for example? So at a city level, to answer that sort of question, you really need local data, and data that is reliable for your local situation, and data which is also up to date. Next slide, please, Mary. So within that context, there are some known issues with traditional approaches to inventory compilation, traditional carbon accounting practices, and I tried to represent some of that on this slide. The word cloud that you can see on the left is illustrating some of the data inputs that are used in traditional inventory compilation practices. And you might see some data types that are familiar to you in that word cloud. But what I want to bring out is that traditional data or traditional practices rely on data sources that are in general not designed for inventory compilation. Inventory compilation tasks repurpose data that have been designed for other domains, and they reform them, they apply assumptions to them, and use them in their inventory practice. So they're repurposed data sets in general. There are exceptions, and we can discuss around that. But they are generally a repurposing of existing data and a simplification, and as such, they represent a simplification, naturally, of the real world situation, particularly when you start to focus on the local scales. Now, some of the consequences of those simplifications you might recognize on the right-hand side of this slide. And those are sort of attributes of existing inventory data, things around the timeliness of that data, the fact that by the time you've got data out of an inventory system, quite often it's at least 2 years out of date. It's things around granularity and whether your national scale picture can translate well to your city scale. And it's things around sort of the update frequency of that data. Quite often you're not in control of the data sources that I'm describing on the left-hand side of this slide. So you can't choose when to update your data, and that becomes an issue when you really want to target particular sources, for example. And also there's things around spatial scales. Inventories in general will deliver at best around a 1 kilometer inventory in a spatial context, and that sort of spatial granularity is too coarse for the city application. And when you're looking perhaps at your net zero plans. Next slide, please, Murray. So at Everimpact, we have taken an alternative view on this, and we've designed a complementary approach that we think gives us and our clients greater and more direct control of the data that we use for calculating CO2 emissions for a city or a territory. And we describe it as a sort of an intelligent data fusion exercise in which we rely heavily on, for example, ground level CO2 sensors, and then combine that data with information from satellites, things around data themes around land cover, city terrain, city topography, high resolution weather data, numerical weather patterns. And we can also combine that with things like ground level traffic cameras and technologies like that. We combine that in a calculation engine to estimate or predict CO2 emissions at ultra high resolutions. And when I say ultra high, we're calculating CO2 estimates at an hourly level and at spatial resolutions which far exceed what we normally get out of a spatial inventory. And using this approach, we think that we can develop data which is better suited for your local needs, more relevant, more responsive to the local situation, and more reliable, and also more recent. And all of those attributes of that we think will generate a better evidence base for compiling a really compelling mitigation plan or net zero plan. Next slide, please, Marie. So looking in slightly more detail into our approach, our method, but still keeping it at a reasonably high level here. We collect a detailed picture of the situation within your city. We use ground level CO2 sensors to characterize the concentrations of CO2 that you experience in your city. We compile information on numerical weather patterns, terrain, buildings, forests and green spaces that you might have in your region or city. And we compile a database to essentially calculate a three-dimensional model of your city, upon which we then predict high-resolution wind flow patterns, wind dynamics. And then once we've established that 3D model and the wind flows, we can apply tried and tested dispersion algorithms to those wind flow patterns and back calculate from the measured CO2 that we're capturing from our sensor network. We can back calculate CO2 emissions, the point of emission and the magnitude of emission using our prediction engine. And because we're doing that at really high temporal resolutions and spatial resolutions, we can then overlay satellite imagery to provide information on land cover and infer from that land cover the likely sources of emissions and the likely source sectors for that emissions because we know the location and the magnitude of the emission. So the output of that process is a series of emissions data layers. The workflow effectively produces a time series of emission broken down by activity sector. So you will have an emissions layer for road transport, for example, and residential emissions and CO2 emissions from commercial and institutional sector, agricultural sector, and so on. And we can slice and dice what sectors those are for your particular application. Next slide, please. Okay, so just to wrap up this section, what I wanted to do in this slide is compare the traditional approach with Everimpact's alternative. And on the horizontal axis of this slide, we've got some attributes of an inventory data set, let's say, and on the verticals we have the properties of traditional inventories and our new measurement-based approach. So taking spatial resolution as a case, I've already mentioned we can traditional inventories deliver around a 1 kilometer square meter spatial emissions inventory, and with our approach we can significantly improve that down to a resolution of 0.002 of a square kilometer. So vast improvements there. And in terms of data timeliness, if we take that traditional view on the timeliness of inventory data as it stands, it's around about 2 years old by the time you get it. Whereas with our approach, because we're using near real-time sensor data, although there's a time lag because we need to do some calculations on those sensor data, we certainly believe that we can generate a monthly time series, or we have, as we will demonstrate, developed a monthly time series, and we think we can get that down to weekly, daily, and possibly even hourly with some more work on our side. So significant improvements there. We're talking about a real-time time series of emissions with some lag, obviously. And in terms of reporting, because all of our data is machine readable, all of our data is stored in a database. We can work with you in terms of your reporting requirements up front, and the reporting then on a annual or periodic basis becomes a button press. So we think that ongoing reporting costs become far less with our solution, and we can provide access to that report via a dashboard or a data API, for example, if you want to consume the data into your own systems. And importantly, that last horizontal access to finance, because our data is more locally focused, it's more relevant to your specific local needs, it's more responsive to the changes that are occurring at a local level, and we believe it's more reliable at a local level and certainly more recent. We think all of these attributes help to unlock access to finance pathways, which I think we'll talk about in subsequent sections of the webinar. But our data, our evidence base will allow you to unlock that financing. And with that, I'll hand back to you, Mary, for the next section.
Sure. Thank you, Tony, for talking us through the different reporting approaches. Now let's look at how this works with a real city and in the city of Dijon in France. So I'm going to hand over to Pete for the demo. Just to give you a bit of context, while Pete is loading his demo and sharing his screen. So Dijon is in the eastern part of France, 250,000 people, and an area of 240 kilometers square. Dijon is also a pioneer in terms of climate action, and they are part of the 100 cities selected by the European Commission to join its Net Zero Cities initiative. So over to you, Pete, for the demo.
Thanks, Marie. So yeah, as Marie said, the demo that we're going to show you today is based on work we're doing with the city of Dijon in the area of Burgundy in France. There's about 250,000 inhabitants across 240 square kilometer area. Now, what you're looking at the moment is our web application. It's what we call our Everimpact dashboard. And this is available to you as users to get instant access to data that has been gathered across the given defined area. Now, the work we did with Dijon, it was decided that what you're looking at on the map at the moment, that was going to be their defined area. That was their area of influence. That's what they wanted monitoring. So what we're doing, as Tony mentioned, we're using a combination of ground-based sensors and aggregating that with satellite data to give the dashboard the look that it's got at the moment. And what we're demonstrating to this particular customer is the attribution of CO2 emissions to a given location within the city limits, the defined limits that the city gave us. And we can define those emissions to a specific source within the city. So as I mentioned, there's 75 sensors. They are strategically located. So a planning exercise was undertaken with the city to define where those sensors would be located. And once they were installed, we can then start the work of aggregating that data that they're sending to us, along with that satellite data, and starting to build that into the dashboard for the city officials. So what I'm going to do now is I'm going to start to zoom in on a specific area. And as I just move my mouse over, you can see on screen, as I'm hitting a particular location, it's telling me in tons how much CO2 in that little pop out for that given location. And that will become more apparent as I start to zoom in on a particular location in the city. So I'm going to continue my zooming in on the screen. And you can see that CO2 is showing up really as hotspots across the city. Now, if I want to change the look and feel of this, I can start to change the opacity of the overlay on the map. So I want to look at a particular location. So let's pick on that main road junction between the A39 and the N274, which seems to be a particular hotspot. So I can zoom in and just see, based on the colors, where that hotspot is. And as you can see, it's very much in this location here. Now, there's a key in the bottom right-hand corner, which is telling you on a color basis the number of tons based on the color. And this is a very, very high hotspot in this particular location. You can see in here, there's a flyout on the left-hand side that's showing you a monthly breakdown for the whole city. So we're pretty much close to 2 million tons of CO2 on a monthly basis coming from the city. And I can pick that data out on a monthly basis based on that chart. If I scroll down, there's a pie chart here that's dynamically built based upon the sectors that have emitted that CO2. So as a city as a whole, the over 50% is coming from residential. The next section, the next highest emitter is road transportation. And that's the city as a whole. So what I'm going to do is I'm just going to push that back in, and we can zoom in on this specific area. And what I can show you now is, as we zoom in, you'll start to see a series of hexagons. Now, those hexagons denote a 200 square meter, as Tony mentioned earlier on, 200 square meter area. Now, as I zoom in, I can click on those particular locations and I can start to build up a total. So if I fly the board back out on the right-hand side, it's not showing particularly clearly. So if I just zoom that opacity out on here, we can see in the pie chart at the bottom, there's 1,143 tons in that particular selected area of what I've selected on that particular road junction. Now, this would be particularly important if I'm a city transport officer or a city finance officer. I'm looking at ways of minimizing traffic through a particular location. I might be wanting to invest in a public transit scheme that's going to mitigate the number of vehicles coming into the city. If that's a residential area, I can be looking at the emissions from maybe social housing because I want to implement a project of insulation for public housing. So what we're able to do is attribute the exact amount of CO2 on a monthly basis to a very, very predefined area. And as Tony mentioned, existing inventories, the data is always at least 2 years old and isn't able to attribute to a particularly close location. As Tony mentioned, it is too coarse, those existing inventories, and we can narrow that down to a very, very tight location. And then we can accumulate various others. So as I do this, those numbers will change in the pie charts on the left-hand side. So I'm just going to push that back in. I'm going to zoom out. So I might want to, as a project, I might want to look at the CO2 that's been emitted from all of the junctions on a particular road. So that might be here, then I could do the same in this particular location here. I could do the same as that ring road going right the way around the city. What we can do with that data is then we can report on it. So we can click on here, we can define a particular report, which you can then deliver to key stakeholders across the city or to external stakeholders from finance, central government, etc. The last thing I just want to mention on here is we also have an open API. So you can take the core data for your city directly out of our platform and into your city management solutions that you may already have. Now, that might be a traffic planning solution, it might be a finance solution, it might be an ERP, or any other business tools that you're using within the city at the moment. You can take the data directly out of the Everimpact platform through our API and then do something meaningful with that data to help with improving the lives of citizens across the city that you happen to be representing. So that's the demo. With that, I will hand over back to Marie.
Yeah, where just under 2 million tons, okay? 2 million tons, and that's based on the area and the scope 1, okay? If we compare this to a top-down approach where, for instance, we were going to do multiply the population of 250,000 people times the average carbon footprint in France per capita, which is just around 9 tons, we would land at around 2.3 million tons. Okay, so which means that our direct measurement is commensurate with this top-down approach. However, if we look at the bottom-up approach, the traditional carbon accounting approach that Dijon is using, the city's current inventories are about 0.8 million tons. So there's essentially a huge difference and a huge gap in emissions being reported by the city teams. So we know, because we speak when speaking to them, that there are some freight emissions that they can't really monitor. We know that these also include some energy emissions and some further scope 3. But however, there is a huge gap. So I'll leave you to draw your own conclusions on whether this is a challenge or an opportunity. But we believe on our side that this is really a call for complementing traditional estimation-based method with direct physical and real-time measurement. So now we've been talking about emissions, but there's also an interest in monitoring your sequestration, because if you want to reach net zero, you will also need to maximize the sequestration of your natural carbon sinks if you have fields, and in particular forest and green space. And these will also come with some side benefits, co-benefits. So I will hand over to Alain to present how we also do this in the city of Dijon and in a specific case study in Japan. Over to you, Alain.
Thank you very much, Marie. As an introductory sentence, I would say that when we're talking about achieving carbon neutrality at the city level, we need to be conscious that it's a huge challenge. And in the case of Dijon, our first estimation, taking the surrounding area of forest, I mean, we hardly detect more than 20,000 tons per year sequestrated, as opposed to the 2 million that the city is emitted. So let's be honest, and let's keep in mind that in order for the city to become carbon neutral, they will have to engage, and there is a great need of securing further carbon sequestration in large areas of forest. So, and of course, we do that at Everimpact, and we do that in a mode that we are trying to that we have elaborated over time, which is basically with the sense of achieving the best cost benefit possible by arranging different sources of data and integrating them. So our approach lies mainly and first of all on the satellite imagery that we analyze in different ways, actually, and in long-term series. So we are able to look at the land use evolution, but also at the vegetation evolution over time by compiling long-time series of 20 years of satellite images every 10 days. So it's a considerable amount of data that allow us to have a trend for every pixel of roughly 30 meters by 30 meters. Then, of course, you need to compile all this information with the forest inventory, and then there is, of course, a modeling part that we do, which consists in using those inputs from satellite imagery and the forest inventory together with the climatic data to solve all the equations that are governing the exchange of carbon between biomass, atmosphere, soil, above ground and below ground. And ultimately, we integrate the climate change scenarios, so in such a way that we can come up with a simulation of the carbon sequestration, not only based on the actual situation, but also with the retrospective and the prospective carbon sequestration, which allow actually to somehow integrate in our calculations the eventual increase in the vulnerability of the forest due to climate change. So our approach provides us a way to have more secured carbon credits to offer to the off-takers. And of course, we are a strong experts in satellite imagery and big data, but we also know that we need to be cautious, and we always anchor our calculation and modeling based on ground data that we collect ourselves directly. So this is now what is our approach looking like in a concrete example in Japan, in northeastern part of Japan, in the prefecture of Miyagi. And of course, from the forest inventory, we've got the 3 characteristics in terms of age, diameter, height, the species, therefore the tree biodiversity, the storage and density of trees, the vegetation index, the leaf area index, which is basically the total area that is available for captation of solar radiation to transform that into sugar and ultimately in lignin and therefore unstable carbon in the biomass, and other indicators related to biodiversity in terms of presence of flora and fauna. Regarding looking at the sequestration performance, we are able to actually calculate, determine what is the CO2 equivalent removed and emitted by respiration for each polygon of roughly 30 meter by 30 meter. We could do that at a higher spatial resolution, but 30 by 30 is a very good cost-benefit compromise. So it's the reason why we're sticking to that. A tree carbon stock is also evaluated per hectare. And soil carbon stock is also evaluated and expressed in CO2 equivalent per hectare. Okay, so this is the case study that we have done for that we are still working on actually now reaching the stage of submitting to the international standard Vera a full project description document. That is the document which is required. So our client is Hitachi Systems, which is a branch of this very well-known Japanese conglomerate. And they work in support actually to the local governments in Japan to support sustainable development in general, but in particular the regeneration of the huge area of forest that they have there. And their client, a local authority, were looking for a solution to monitor and optimize the health and the stability of the carbon sequestration over an initial pilot area of 3,900 hectares that is now, as we speak, extended to 20,000. So in order to provide this forest monitoring solution, we have used the best satellite imagery available. We have mobilized expert carbon and biomass analysis. We have also modeled and integrated the climate change impact modeling in our calculation, and we did an in-depth knowledge of sustainable forestry practices in order to select and recommend to our end users what are the techniques and the protocols that may lead to a quick regeneration, increase in climate change resilience, and ultimately in carbon sequestration performance. And all this data is available through an API, which is actually hosted directly accessible from our clients' websites. Actually, at the very beginning of the project, the first very simple thing we did was to compare a summertime satellite image with a winter time, and this has allowed us to make the difference very easily between the conifers, which are evergreen, and the broadleaf forest that are losing their leaves during the winter time. And of course, the problem there is not that much the natural forest composed of broadleaf trees, but mostly the conifers, which is the Japanese cedar mainly, Cryptomeria japonica, who has been widely planted in the early 50s and 60s. And now all those forests are arriving at the same maturity, aging, and of course, this is not sustainable over time. So there is this need of restructuring the forest, and it's what the carbon project is about. With satellite imagery, you can do a lot of things, and especially this is to insist on the value of looking at satellite imagery, not only from as a substitute of aerial photograph, etc., but that you can also use those satellite images to determine long trends of key variables, like in this case the vegetation index and DVI. And you can see here that with this series of maps that you see, we can see what has been the average sequestration dynamics per year. And you see that some years have been extremely favorable and others have been too dry to perform, actually. So this is the proof that not only there is the carbon sequestration is not a linear phenomenon, but it's very much linked to the climate condition, and therefore highly dependent on the evolution of the climatic variables. So it's the reason why we use this type of I mean, this is an illustration of the evolution of key parameters. Here we are looking at a temperature over the French territory according to the IPCC scenario. And you can see that actually there is an expected increase in the average temperature of up to 5 degrees. We did the same exercise for the Japanese forest I've been showing. And as a matter of fact, we saw that the rainfall is likely to become more or less stable, but the temperature will rise, meaning that the forest will suffer more and more in the summertime, and the exposure to forest fire is likely to increase. So of course, this is a factor in our calculations, and we are able actually to predict the carbon balance and differentiate from the type of forest we are talking about, and therefore give as good as possible indication to our end users on what they can expect in terms of sequestration and what they can do to improve that and also taking into account the reduction of the exposure of those forests to the, to the climate change. So in terms of just to give you an insight on what were the operational conclusions of all this exercise, is that in fact we have observed in the ground that there is that in fact what we have detected on the satellite imagery revealed to be true when we visited the forest. First, that there is a loss of diversity, that the forest is aging, is now 70 years old, and of course the photosynthesis activity is declining. We also found out that the inventories, the official inventories, forest inventories, were incorrect, and we were able to correct them thanks to the satellite imagery. We also found out that with the climate change modeling that we are to expect a drier condition in the near future. We have been able to establish what is the current carbon sequestration rate and simulate what is likely to be the carbon sequestration in the future, with and without the mitigation measure that we are recommending. Mainly intervention required to remove all the trees to make space for natural regeneration, plant younger trees to increase sequestration level and biodiversity, and ultimately regenerate the forest with the introduction of broadleaf species. We are actually complying with an approved methodology by the international standard VERA, and we expect, we have listed the project just before Christmas, and we expect to have the project register and the volume of carbon credit that goes with it validated in the end of summer. Thank you very much.
Thank you, Alain. So this is a really good example to complete the Dijon one on how we apply also advanced carbon monitoring to carbon sinks to maximize sequestration of green spaces to achieve net zero targets, whether you're a local community and authority in Japan or in Europe. So thanks for this demo, this case study presentation, Alain. So now I'm going to hand over back to Pete to explain how this better understanding of carbon can help unlock new sources of funding to decarbonize cities and transport.
Thanks, Marie. So as you've seen so far, cities are very, very reliant on data to try and put into action improvements for the lives of citizens, but also to unlock sources of finance that wouldn't necessarily be previously open to them. So what we are able to provide is highly accurate data, and that is what the green finance industry are looking for, is very, very detailed information around your city or your project, in order that you can gain access to financing at better rates. Now, I'm based here in the UK, but this is very similar globally. Cities are under extremely harsh pressure financially, trying to do more with less. So gaining access to financing to implement projects to improve the lives of citizens across their cities is an ongoing challenge. So if we're able to demonstrate a way for a city to access green bonds and loans, or access the carbon markets, where it's able to utilize natural resources within the city's boundaries to raise capital to implement projects, that's a virtuous circle as far as the city customers that we have are concerned. Can you go on to the next slide, please, Marie? So just to conclude on this and to bring us home, the key in everything that we're doing is the ability to verify data. This is live data, rather than relying on old inventories that are currently being utilized in many cities across the world. So what we're able to do is give you very highly accurate historical and forecasted data that allows you to gain access to those carbon markets. For the finance organizations, it's minimizing their reputational risk. They want to be investing in cities that are able to provide them with the most up-to-date information, and then are able to offer the best rates. Urban decarb project owners are able then to utilize this data across all of their key stakeholders, both inside the city and outside the city. I referred when I was doing the demo to the reporting capability. Incredibly in-depth reporting can come out of this that can then be shared. It's your information. You share that both with internal key stakeholders, but also the finance organizations that you can go to gain access to those sources of funding that wouldn't necessarily be open to you through central government budgeting for your particular city. That way, if you want to have a project to do an urban transit scheme, or installation of homes, or the utilization of brown field sites across the city, those projects may be able to be achieved through access of green funding through the carbon markets or through green bonds and loans that you wouldn't necessarily been able to access had you not had access to the data. And we're seeing a huge uptake in cities focusing on accessing those finance channels recently. And that's what Everimpact as our solution is able to assist you in doing. So with that, Marie, I'll hand back to you.
Thank you. So just to conclude before we take some questions, these are for us the main benefits of real-time, granular and direct emissions measurement. It's about accurately monitoring carbon, and this also includes transport and nature-based solutions. It's about ability for you to track and communicate your decarbonization progress at the city level. And you can do this for your stakeholders, your citizens, your partners, and also for people that are supporting you on the finance side of things. So when you can prove your plans, your policies have impact, it's much easier to gain access to green finance. Thank you again for your time today. And do feel free to get in touch with our teams if you want support to accelerate the decarbonization of your city.